Today we're diving into one of the most fundamental concepts in all of physics, gravity. But this isn't your standard textbook lesson. We're looking at a huge clash of ideas, a showdown between a century-old champion and a brand new challenger that claims everything we think we know might be completely wrong.
So let's get right to the heart of it. What if our entire concept of gravity is backward? Is it just a passive thing, a weird quirk of geometry in the shape of space-time, or is it an actual physical force that actively pushes things together? That's the core of the whole debate we're unpacking here.
In one corner, you have the heavyweight champion for over 100 years, Einstein's general relativity. It says gravity isn't a force at all, but just what happens when mass and energy literally bend the fabric of space-time. And in the other corner, you have the challenger, graviton pressure theory. Now, to be clear, general relativity is the bedrock of modern physics. This challenger is definitely coming from the fringes, but our goal today is to really explore the arguments behind its challenge, to understand the debate itself.
And let's be absolutely clear. According to the source for this explainer, these two ideas aren't just a little different, they are fundamentally irreconcilable. We're not talking about a minor disagreement. This is a proposed total break from the past, a choice between two completely different versions of reality.
Okay, so let's quickly recap the champion's take. General relativity sees gravity as, well, passive geometry. You've probably heard the analogy. Picture a big bowling ball on a stretched out rubber sheet. It makes a dip, right? A curve. Now, if you roll a little marble nearby, it's just going to follow that curve. The marble isn't being pulled by the bowling ball. It's just following the shape of the space it's moving through. Mass makes the curve. The curve tells things how to move. Simple as that.
The challenger graviton pressure theory just throws that whole picture out the window. It suggests a physical mechanism. It asks you to imagine that we're all swimming in a cosmic sea of tiny particles called gravitons, and they're pushing on us from every direction all the time. Now, a big object like the Earth acts like an umbrella, blocking the particles coming from below. This creates a pressure shadow, and the result is a net push downwards. That's what we feel as gravity. It's an active force, not just a passive path.
And this right here really gets to the philosophical divide between them. General relativity is like a perfectly detailed map. It can describe how a planet orbits or how light bends with just incredible accuracy. But its critics say it never actually explains why any of it happens. Graviton pressure theory, on the other hand, claims to be the engine itself, the actual physical mechanism that makes the whole thing go.
So, the real test is how do these two competing ideas hold up when you throw the biggest mysteries in the universe at them? Let's see how each one tries to explain three of the biggest head-scratchers in cosmology.
First up, the mystery of galactic rotation. When we look at galaxies, we see the stars on the outer edges whipping around way too fast. Based on all the stars and gas we can see, there just isn't enough gravity to keep them from flying off into space. So, what is going on?
General relativity's answer to this is dark matter. It's some kind of invisible, totally undetectable substance that's providing all the extra gravitational pull. Now, the folks who support graviton pressure theory say this is just an unnecessary patch. They argue that the spiral arms of a galaxy actually channel the flow of gravitons, creating these pressure corridors that naturally push the stars along at higher speeds. No extra, invisible matter needed.
Okay, next up, gravitational lensing. We've known for a long time that light from distant galaxies will bend as it passes by a massive star or another galaxy. It's actually one of the most famous proofs of general relativity. But surprise, surprise, these two theories explain it in totally different ways.
The difference in the analogies here is really striking. With general relativity, the light is just following the shortest possible path through a curved spacetime. It's like that marble rolling in the groove made by the bowling ball. But graviton pressure theory offers something you can almost touch. It suggests the graviton field is denser near big objects. So just like a straw looks bent when you stick it in a glass of water, light gets refracted as it passes through this denser medium.
And for our last big comparison, time dilation. It's a fact that clocks tick slower in stronger gravitational fields. It's a real thing. We actually have to adjust for it every single day to make our GPS satellites work. So why does it happen?
Well, general relativity explains this with something called gravitational potential. Basically, time itself just runs slower the deeper you are inside a gravity well. The Challenger theory, though, it proposes a much more direct cause. It argues that a denser graviton field creates pressure resistance, which physically slows down the atomic vibrations that our clocks actually use to keep time.
So after offering its own explanations for these cosmic mysteries, graviton pressure theory kind of goes on the attack. It lays out what it calls a final test, a series of direct challenges aimed right at the heart of general relativity's foundations.
So these are the 5 big questions its supporters claim general relativity just can't answer. First, what's the physical cause? How does a chunk of matter actually tell space-time to curve? Second, what's the medium? If gravitational waves are ripples, what's the stuff that's actually rippling? Third, how does energy transfer? How can an abstract shape, a curve in geometry, impart physical energy to an object? Fourth, the Newtonian problem. If gravity isn't a force, why do GR calculations still rely on old-school, force-based Newtonian physics? And finally, structure. How does the theory account for the internal structure of an object, not just its total mass?
And this all brings us to the real crux of the argument. The debate, as it's framed here, isn't just about which theory makes better predictions, it's about what we should expect from science in the first place. Should we be happy with a perfect description of what happens, or should we demand a physical explanation for why it happens?
There's this quote from the source material that just nails the difference in mindset. General relativity, it says, invites us to admire the beautiful static sculpture of curved spacetime, but graviton pressure theory invites us to actually shape the field, to interact with it, and maybe, just maybe, even engineer gravity itself. And that gets us to the ultimate trade-off being presented here. Look, nobody denies that general relativity is an absolute masterpiece of prediction. Its math has been proven right again and again and again. But the challenger is basically asking, is being right the same as being true? It wants to replace a model that works with a model that it claims explains why it works.
So we're going to leave you with this question to chew on. As we try to figure out the universe, what's actually more important? Is it having a theory that gives us the right answers with stunning precision, even if we don't know the mechanism? Or should we demand a theory that explains the cause behind every effect, even if that means questioning 100 years of established science? The answer to that could really define the entire future of physics.